Hi, this is Chan Beauvais, your instructor for CIS 209 Relational Database Concepts. This is a topic that's near and dear to my heart. We've been storing data in relational format for about 45 years or so now. It seems to be the best working format for storing data without winding up with inadvertent duplication and redundant data. So we're going to go through the concepts behind relational data. Our objectives for this topic, we want to define what a relational database is, discuss what this thing called an entity, or in algebra a relation is called, what are the attributes that describe the entity, what types of relationships can entities have with each other, and then what are the different types of relationships that entities can have with each other. In 1970, a guy named Ted Codd, who worked for IBM, proposed in a document called a relational model of data for large shared data banks, a way of not treating data as if it were in a file system and processing it row by row. People were reaching upper limits of functionality in terms of being able to handle large sets of data because they were forced to treat data sequentially or in one row at a time processing. So Ted Codd was a mathematician, and he said, let's treat these things like algebraic sets. So he proposed 12 rules. We're going to distill those rules down to the ones that have to do with data modeling and data storage. So the fundamental rule is that data gets stored and retrieved from what are called relations, and this again comes from algebra, relational algebra set theory actually. Another name for a relation you're going to see throughout, and we're going to kind of shift away from the term relation, would be entity. So we're going to be using the word entity here as a really just kind of the same thing as relation. So a relation is comprised of rows, which were called tuples, and then attributes, which wind up being the vertical structures within the two-dimensional table. So here are the 5 things that really matter. There are 6 or 7 of these, but kind of distilling them down and adding them together. So the rules for a thing to be a relation, for a data set to be a relation, is that each row must be unique, therefore representing a single instance of a relation. So if we're talking about all of the students taking this class, and we have a student relation, each instance of a student would become a row, a unique row, within that relation. Each piece of data, and by the way, that data is the plural, datum is the singular, so each cell, the intersection of row and column, must have a single value in it. You can't have a comma-delimited list of values or more values than belong in that. So for instance, if we have name, we might have it separated out as first name and last name, but we would keep it single-valued. We would put the first name in the first name column, the last name in the last name column, and therefore we are relational at that point. One of the interesting parts is that the order of rows and columns doesn't matter. It is immaterial. So that it doesn't matter which columns come first or which rows come first. As we do our querying, we can order them, but innately, it doesn't really matter which column comes first or second, which row comes first or second. And here's another really important one. Field names are unique within a relation. So you can imagine if you were writing a query and you said, get me name from the student table, and you had 2 fields called name, how would it figure out which field to return? So the field names must be unique within a relation. Now, when we get into doing some querying later, you'll see that you may join 2 tables together, and if both tables have a field of the same name, you'll have to put the table name or an alias to the table name in front to make them unique. And lastly, data within a column belongs to that column's domain of possible valid values. So that's what a domain is. It's a set of possible valid values for an attribute within a set, within a relation. We might have birth date. So the birth date would be all the possible dates. The oldest living human is 114 years old, so it couldn't be over 114 years old, and it certainly can't be in the future. So those would be the domain of possible valid values for a birth date. So rows, the horizontal things that go across, are known as tuples. I for the longest time pronounced this tuples and was corrected. It's actually tuples. Each row is somehow unique, not duplicated exactly by any other row. And we'll use what we call a primary key to enforce this later. Towards the end of the deck here, we'll talk about primary keys. And then columns are the vertical things known as attributes or fields, and they hold the data elements that we have for each row. Within a given column, it has to be the same data type. So if a column is a date, like a birth date or a date of employment, termination date, date deceased, those all must contain dates. If it's an ordered quantity, it must all be numeric. If it's a shipped quantity, probably always numeric. So every instance going down vertically down that column must be of the same data type. Here's an example of a relation about student. So you'll notice that there are 5 columns and there are 3 rows. The first row, of course, is the header, showing you what the field name is. So within student ID, all of the rows for that column will all be numeric data. The student name, again, we're just doing this as an example. We should probably have first name, last name broken out, but just for this example, we would have text data. Student's date of birth, we would have date data. The student address would again be textual data. And the GPA would be numeric data. Now we'll get into refining terminology a little better. So a table is defined as a two-dimensional matrix of rows and columns. When we get into some more advanced studies in data warehousing, we'll see that we can build cubes, which are n-dimensional. It could be 3, 4, 5, 6, 7, 8-dimensional. But relational, we're dealing with 2 dimensionals, rows in one dimension, columns in the other. And one of the most important things to understand about a relation is it is about one and only one thing, sometimes called a theme. As soon as you start mixing themes, you're going to wind up with an improperly designed relation. So they typically are object-subject based. For instance, student, instructor, perhaps a course, a school, something about which we're going to store data. They could be event or transaction based, and the key with that is those occur in time, but they still are things we store data about. We have another classification of lookup or validation based, where a lookup might classify things. For instance, if you're in the CIS program, you're taking CIS 209, well, that CIS thing is actually the computer information systems. So that's a lookup of a category of class. Validation is more like a valid value list. So if you have days of the week, you'd start with Sunday, end with Saturday. Those would be in a list and probably present themselves as drop-down lists on user interfaces. So the way I categorize these is subjects are the main things that we track. The subjects then are involved in transactions or events. And lookups will provide, like the categorization, as I mentioned, or a valid value list for either a subject or a transaction. Talking about a field or a column or an attribute, it's something, a chunk of data, a characteristic that describes the entity that it's associated with. So it could be, for instance, a product might have a color, a size. A person might have a name, an address, some chunk of data about the entity. And contains one and only one chunk. Again, no multi-part like address, city, and state being merged together, or multi-valued as a repeating group of common delimited values, as you can see, 12, 14, 15. And we're not going to store calculated values in our fields because we can construct them at runtime with a query. So when you do include calculated values, you're doing the thing called denormalization, and we'll talk about that at some length later on. So some more terminology. A field is also called a column. We'll have a data type that describes what kind of data goes into the field, the type of data goes into the field for each record. For instance, you may have a date data type for something like date of birth or date deceased or employee hire date. Those would all be date data types. If you're talking about an order, you might have a quantity of a product ordered. That would be a numeric data type. You have a domain of values for the field. There's a business rule-defined set of possible values. So a domain could be shown in a drop-down list of valid values, like for instance you see in a website where they ask you for your expiry date. They may ask you for a month field, which would be 1 through 12, and then a list of years, which is usually current year through maybe 5, 10 more years out. There could be business rules like when you hire someone, you can't hire them unless they're at least 18 years old. If you had a maximum retirement age, you couldn't hire someone whose birth date was before that maximum retirement age rule. Numeric data could be an ordered item quantity, might be have to be in a whole number, may have to be greater than 0. We wouldn't let somebody order 0 of something. Might have to be less than 500 or 1,000, but again, we're talking about the analytics here, the analysis rather, of gathering these business rules and analyzing them and making sure they comport to each other. But this is a business rule-defined set of possible values. That's the biggest part to understand. All these rules come from the business. A database analyst should not just be making stuff up. That should be self-evident. So again, getting back to your business analysis work and making sense of it. Now for those horizontal structures, they're records, also known as rows. Again, we'll be using these terms interchangeably, row and record. It contains a single instance of an entity, again, a student in the student table. When we get into physical design, it will represent a row in a table. The set of all the rows comprises a set of students. So all the student records become the set, again from set theory in algebra. Each enrolled student would have one row in that set. A record in one table, however, may be related to records in another table. If we're keeping track of each of the courses that a student takes via a class that's offered. That class would be offered in a particular quarter. The student would enroll in the class, and therefore the student record would be related to all of the enrollment records in the classes they had enrolled in. So relationships are actually one of the most important things about relational database, but amazingly, the word relationship is not what relation is about. Relational database is about the fact that we're dealing with sets of data which are algebraic relations. So relations are usually, and almost always, related to other relations or entities. There are three fundamental types of relationships we'll get into in the next slide, in the next topic. But they are one-to-one, so we might have an employee and a parking slot, and the employee is assigned to one and only one parking slot. A parking slot is assigned at any given time to one and only one employee. The most frequent type of relationship we'll find is a one-to-many. So a student may have many contact numbers. A student may have many addresses. Right? A course may be taught in many classes which would occur in a particular quarter and have an enrollment. And then many-to-many is also very common. For instance, the student enrolling in many courses, and a course can enroll many students, so you wind up with the many-to-many relationship as well. Those are the three typical types of relationships we find. One of the important things to understand is we must think about them in terms of an instance of an entity A being related to an instance of entity B. So a customer can place many orders, customer being entity A and the order being entity B. We'd want to reference them in both directions, so we would say one customer can place many orders, and many orders would be placed by one customer. And finally, in this topic, we want to talk briefly about keys. We'll cover them much later as well. Two main types of keys, primary keys and foreign keys. So there are other types we'll get into a little bit later, but generally primary keys and foreign keys are the big hitters. So each table should or must have a primary key. It uniquely identifies the row and therefore is one of the rules for relations satisfied. The value in one or more fields would be generate a uniqueness. So when you're talking about keys, you might say the student could be uniquely identified by their phone number, unless two students are sharing the same phone. They might be uniquely identified by a student ID. They might be uniquely identified by some other combination of fields. And they can be from the domain of data, or they could be system generated. So we'll talk about the two types of keys, natural keys or generated keys, called surrogate keys a little bit later. Foreign keys only go into many-side relations within a relationship. And the foreign key is a column that contains a copy of the value for that row that it's on, that links it back to the one-side entity. We'll talk about this in great depth later on. But that's how we link tables together. And when we go to query, we'll need to be doing those kind of links. We'll call them joins. So more on that later. And this is all we have for this topic.